Let's talk about some of the near-term features that we're working on for the projects platform. So since it's a task management platform, obviously you're going to need to manage tasks. So we've chosen like a Kanban-style project tracking for that. So you have statuses, to-do, in progress, etc. There's going to be multiple users. So we're going to support teams. Teams are going to be having users, and you should be able to collaborate with each other in the comments. We're going to have advanced task management, so tasks can have dependencies, like in Jira, and you can create, in Jira it will be called epics, things that have multiple tasks, so you can have a big initiative that has multiple tasks. Different members will have different kind of access control, and there's going to be a generic tagging system to organize the tasks. So for our database, we decided to use Supabase because it's very robust and extensible. We had some alternatives, but Supabase turned out to be the best option, just because of its pricing model and its robustness and the sort of sentiment in the community. Firebase for the software, backend software. Postgres for storing user information and tasks and things like that. And obviously, it has a REST API for the front end. Okay, I think, yeah, you can see the database tables. So I won't go too much into the details of every single table, but yeah, we have a generic resources table with a tasks table. So that maps to your artifacts. So let's step back for a second and talk about artifacts. So artifacts here means anything that comes out of your ML task. So be it models, data, features, and these will be stored in a cloud storage, and they'll have a path to them. And we want to sort of keep track of these in the projects platform so that, let's say you're just going through a task, someone has completed it, and there's deliverables. They can easily just link these artifacts in the projects platform, and you can use them in the future. The access control system is pretty simple. You just have different users assigned to different projects. You have users assigned to resources, etc. Comments are also pretty self-explanatory. You can comment on projects, you can comment on initiatives, and you can comment on individual tasks. The API uses some endpoints for authentication. So you have registering and login, getting users, updating, adding, deleting users. The project's endpoint also has get create. And for tags, we haven't exactly mapped out the details of what tags we'd like to have. This is up to the projects themselves. But we're going to roll it out with some set of basic tags. And then hopefully in the future, we can create some functionality where projects can create their own tag. Let's now get into the front-end design. So on the left here, you're going to have a bunch of projects. You can have a very compact Kanban board. The idea here is that if you have used like GitHub Actions, or not GitHub Actions, GitHub Projects. GitHub Projects also uses a Kanban style. Jira is slightly more advanced, but we wanted to keep this simple for our projects, and eventually we'd like to have a calendar and a Gantt chart. So the front end uses Next.js, supports different API routes, offers middleware, fast and efficient. Most of our team members have used this in the past, so this was a very familiar piece of technology. And we're using the Vercel cloud platform because of its free offering for hosting our platform. This is the design of the Kanban board. And you can see it's pretty minimalistic, and I think we'd like to keep it that way so that it's simple. These are just the different menus. You have creating new issues and sharing the project. And lastly, aside from these initial features, we'd like to have a large, sort of a very ambitious feature outlook with this platform because of the model and data lifecycle stuff. So ideally, both the compute platform and the projects platform have APIs. So we should be able to access these from each other. So when let's say you're working on a task, and let's say the task is train a model. You should be able to trigger that training job from the projects platform. And if the project platform keeps track of your model your model version and your dataset version and features version, you can specify which of these versions you'd like to use. And that's the real sort of offering that we have, is that you can have all of these resources on the same platform. Um, I think, yeah, I think I'd leave it at that for projects platform. And thank you for listening. If you have any questions, please feel free.
Okay. Thanks for the presentation. So, one thing I'm wondering about is what the AWS changes over time, and also the AWS business model, I guess, in terms of, for example, selling spot instances, and those against what we're trying. So, how do you think about evolving projects as AWS changes?
So first thing to consider is that we're not necessarily locked into AWS, right? Every cloud platform has an API, and you can easily write sort of a connector between that API and your platform. So we're not locked into the platform. And if it does change, we plan to sort of design further and enhance the platform to sort of change with their business model, I guess. Like if they said we're no longer supporting spot instances, well, I guess we can't use AWS, but if they have another offering that lets us minimize cloud costs, we'll just switch to that offering.
I think it's not so much we no longer support spot instances as the entire business model is not make spot instances easy, right?
Right, okay. Yeah, in that case, we'd have to switch back to on-demand. But we'll still find a way to minimize cloud costs. Maybe have our own sort of architecture that manages those spot instances. Yeah. Hmm?
When you talk about spot instances and your plan to integrate them, and so they're definitely cheaper, but how do you plan on dealing with job preemption when spot instances get preempted on the task?
Yeah. That's why we want to have multiple cloud platforms, so that if one platform doesn't have enough instances or you don't have enough resources there, and then we switch. Mm-hmm. Right, okay. Yeah, so you're going to have metrics and reporting. So you're going to be saving your model checkpoints, right? You're going to be saving how much of the data have you processed. And you can easily pull those back when you switch to a different interface. Now, there will be a slight delay in the area in the aspect that you're going to have to reinstall some libraries, or you might have to reset up some things. But we can probably address that by having Docker images, right?
So is that on you to implement, or is that on the user?
So that's on us to implement the scheduling part where we, yeah. That is not entirely clear yet, but I'd say for now the user, we'll obviously instruct them that, hey, keep checkpointing every this many epochs. But eventually, I think it depends on the kinds of projects that we deal with, right? Because if you have some models that train for very long, right, they might not need like checkpointing very often. But eventually, I think we can generalize that at some level, and then the user will have to take care of less of that configuration. Okay, the question was, how do we make sure if we're, how do we design our user testing and evaluate the usability, right? Okay, so we have one team that has. Sorry. We have one team that is currently trying out the platform, but we just plan to roll out an initial version to a couple of teams and have a questionnaire of, hey, what do you think of this feature? What do you think of like the instructions, say the SSH instructions? And there's some literature on how user testing works and how we can do some A/B testing. In terms of front-end design, the graphical design is pretty simple, I'd say, because we have a lot of platforms to go off of. So, and we don't want to make anything that's too complicated. So we're just gonna stick to that. And in terms of the compute platform, that will have to be changed in the next few months or so, because the project platform will also change. Thank you very much.
Hello. Okay. Hi everyone. So, are you looking for love? Is Tinder not working for you? No luck on Hinge? Well, too bad because this platform is not for you. So, hi everyone. We are the Lovalytics team and we are building a task automation platform and not a dating app. In collaboration with Lovalytics, a data analytics and AI and services company. Who's next? So here is our lovely team. We are a team of students and also recent graduates. And then now for the table of contents, we're going to be walking you through our project objectives, design, and also a demo for the task automation platform. How do I do this? Oh my God. What the hell? Okay. See now?
All right, so basically what we are focusing on is that we found out that business users don't really know how to automate their tasks. And it's due to two main reasons. So the first one is that they don't even know what tasks they can automate. And the second reason is that even if they know what tasks they can automate, they don't know how to actually do the prompt engineering. And for that purpose, we're going to use a database called ONETS to kind of tell us which tasks are automatable. And there's also two main objectives that we're going to have. Next slide. Okay, so the first objective is that we're going to optimize prompting for our users. So no matter what inputs they give it, it's going to create like a clear, good super prompt. And the second basically objective that we have is to build a Gen AI platform that automates tasks from end to end for our users.
So here. So here is our front end design, and as a user, you can log in using your email and password. And once, how do I get on the next slide? And once you've logged in, you'll see our main homepage where you can, I guess, switch the theme, which you will later see in the demo video, and most importantly, navigate throughout your projects. You can access your old projects or create a new project. And once you clicked on the create new project, you will have the ability to set your project visibility to private, where only you can access it, or public, and you can also add collaborators. So here, once you've created your project, we have task suggestions where you enter your profession, and if you don't know what to prompt, some sample suggestions will pop up for you, and here we'll show which tasks are automatable or not.
All right, so the plan that we have is that we're going to do the prompt creation using a framework called DSP. So what it allows us to do is to basically give some job context to our framework, and also allow users to input some files so that it will create a very good prompt, like a refined prompt, so that users don't have to go through the iterative process of changing their prompts and trying to make it better so that they get the final results that they want. And when we create that prompt that we're going to call super prompt, we can feed it then to our like task execution that are kind of made of multi-agent systems. And we're gonna learn more in details about all of these.
Yeah, so for context, DISP is a framework for programming rather than prompting large language models, essentially allowing you to build modular AI systems that, in this case, are aimed to optimizing the prompts that we're creating. There's two main components that we're going to be utilizing in this project. One is DISP modules, and the other is DISP signatures. We are breaking down the prompt creation process into a series of steps, or signatures in this case. A signature is essentially a declaration or specification of input-output behavior for DISP module. For instance, and we're going to be splitting the prompt creation into a series of 4 signatures or steps, from analyzing professional context, analyzing the task context, identifying key considerations, and then creating the actual LLM prompt itself. For instance, our identifying key considerations signature will specify inputs of the professional context, which is the output of another signature, as well as relevant PDFs, and it'll then create or output a list of considerations for the task. We are also using DISP modules, which are essentially abstracting a prompting technique. In this case, we're using chain of thought to link the signatures together. In this case, creating a pipeline where the LM is thinking through each step, creating the overall prompt that we're going to be then feeding into the multi-agent system. We're using 2 modules in this system. One generates the knowledge base, kind of puts all the context together from the PDFs, from the professional context, and the other is the actual prompt generator module that we are utilizing to then feed into the multi-agent system with the super prompt.
Now, once we receive the super prompt from DISP, we go through this workflow, which was constructed in LangGraph, where we first receive the super prompt and prompt it into a task planner agent, which separates it into X amount of subtasks based on the complexity of the tasks that we're giving it. And this is then distributed to the executor agents, which each execute the task, a specific substep that the task planner has given them. And the reason that we're using these multi-agent systems is that by splitting up the main task into various different subtasks, we can reduce hallucination and also increase the amount of detail that we're able to supply the user. Now, after the executor agents complete their tasks, we can pass it into the merger agent, which then merges it into a final output, say a report or an analysis, where we have a beginning, middle, body, and conclusion. And after that, before we finally output that output to the user, we have a verification statement, which based on initial instructions and files that we've retrieved using RAG, evaluates the output based on a set of arbitrary metrics, and then determines whether it's fit to serve the user or not. And if it's not, we go through the loop again.
All right, and now for the demo. Why isn't it popping up? Okay, there we go. So in this example, I am basically just going to be showing how we use our platform to write a simple critical essay. So right here, I'm just inputting a new project and calling it critical essay. And then afterwards, I am deliberately writing a very vague prompt, which is just write me an essay. And the reason for this is just that because we want to showcase that our system can still work, even if the prompt is vague and not very detailed. And then here, we are uploading 2 different kinds of files. So we have instructional files and supplementary files. Instructional files are basically files that we want the entire system to have full access to at all times. And then on the other hand, we have supplementary files, which are basically like knowledge bases, and it's what our task executor agents use RAG to get more information on. So instructional files in this case can be rubrics or outlines, and then supplementary files can be something like, textbooks or books or really long PDFs. And then afterwards, we're just clicking done and then entering our occupation. So right here, I'm putting student. And this is just to give our system a little bit more context into everything, just so that we can tailor a response better for the user. And then afterwards, we click send. And then this is where all of the subtasks are being generated. And here is where the user can just like review the final output and just make sure everything is what they want. They can also edit and delete and add more subtasks if they so please. And then after they're done editing everything, they can click process task with AI. And then this is where all of the task executor agents are executing every single one of the subtasks in parallel, just so that we reduce latency. And then finally, the merger agent is going to merge all those subtasks together into one cohesive output, which then the verification agent is just going to verify just to make sure that it follows what the user wants and also the instructional files that they sent. So just give it a second. And then here's the final output. And as you can see, what's really cool about this is that this was created entirely with GPT-4o Mini just to reduce costs. And this final output, I think, is about just under 2,000 words, which is like exactly what we want because that's what the rubric says so. And yeah, as we can tell, like it's pretty good, which I think Julian is going to elaborate a little bit more on in the next slide.
So the natural next step is comparing the system effectiveness against directly prompting a large language model. So here we use both human evaluation and LLM-based benchmarking. For human evaluation, we focus on word count, output format, and instruction adherence, so whether it actually has proper paragraphs and structure in this case. And on top of this, we also have large language model benchmarking. According to the paper Language Model Council, Democratically Benchmarking Foundation Models on Highest Objective Tasks, benchmarking with collaborative LLMs can actually provide a comprehensive evaluation for writing-based tasks. And so we're inspired by this approach, and we design our own benchmarking system, where an LLM agent with an advanced model, in our case 401, generates custom evaluation criteria based on the instructional files and the prompt provided. Then another agent evaluates the output according to these metrics, after which the average score across the metrics is used for that piece of writing in benchmarking. And now for the results. So each model was given the same task of writing that 2,000-word essay. So if we look at directly prompting, 4.0 Mini, 4.0, and 0.3, 0.3 is slightly better in this regard, but 4.0 Mini and 4.0 especially, like they are completely below the word count in an astronomical manner. 4.0 Mini does not even output proper paragraph, outputs bullet points, and both 4.0 Mini and 4.0 are unable to actually adhere to the instructions in a consistent manner. If we look at the benchmarking score as given by the large language model evaluations, 4.0 Mini is at 37, 4.0 is at 59, 0.3 is at 71, whereas in comparison, our system generates an essay where the word count is 1,965, so just a bit under 2,000. The output is consistently divided into well-formatted paragraphs, and our system has in-text citations as well as works cited, and the benchmark score for this is 83, which is higher than all three models. This is, by the way, running it on 4.0 Mini, which is the lightest model of the three.
So in terms of our major next steps, we'd want to better adapt our system to be able to approach a broader range of tasks in general. Currently, it's mostly good at doing like written tasks. So we want to be able to expand it to be able to approach a broader scope of tasks. We'd also want to continue to add and improve to the features to the UI for our platform. And then finally, we'd eventually want to be able to do some user feedback to make our platform even better. We can take any questions now.
So assuming you have done your market research, how is this product different from what's available on the market?
So oftentimes with large language models, like there's many different fields that they try to use large language models directly to do certain tasks. There's some that are directed towards, say, very specific tasks. However, in the workspace, like for example, I have a friend who's working at a law firm. Even though he's working at a law firm, even if it comes to just dealing with legal documents, there's very many like nuances in terms of the type of task he's trying to perform. So he has two choices, with either one to use a very specific, very specific sort of module that's meant for one type of task that might not fit what he wants, or to directly prompt ChatGPT, whereas he's not in tech, he doesn't know how to prompt things, and doesn't know how to actually use large language models effectively. Whereas with our system, we have both enough flexibility as well enough depth to provide what he actually needs, be it generating certain like brief legal documents or going through instructions and coming up with reports for their clients to sort of brief them on situations, or simply going through hundreds of pages of documents to extract what information is important, because a lot of the times that's also a very important task that many different fields, in his case for like a law firm, that they have to be able to do. So in general, our system is able to provide enough flexibility while also having the ability to go deep enough into any of the tasks that it is automating, which is something that very few other products out there have been able to provide.
So considering you had like about one example about evaluating the prompt that you showed in the example, what are your plans in terms of gathering more evaluation data and actually benchmarking on the effectiveness of your platform?
Well, the natural next steps would be to focus on a very specific task and then somehow acquire enough data that's human generated in that to add to our benchmarking system. Since we're trying to have a benchmarking system that is more general and broadly applicable, this is why we had the human evaluation in addition to the LLM-based benchmarking. So if there are any specific tasks and any specific business application that we would be targeting, we would gather data in that specific regard and then do comparisons with those.
Okay.
Hey, thanks for the presentation. So one thing I noticed in the example that you've shown is that, in a way, you did supply the prompt that was the rubric, right? In the value proposition that I think you introduced at the start of the presentation, I think the big thing was, well, what if I don't know how to write the prompt? So how would you generalize this to a situation where you don't have the rubric?
Yeah, so in the situation where you don't necessarily have the rubric, that is when the prompt creation and the actual context, the professional context and the context of the task comes into play. So that all comes into play during the prompt creation process. So for example, in that case, let's say we didn't have a rubric PDF that was uploaded to kind of give it more of an instruction. Given the task itself and the professional context, in the prompt creation step itself, it will generate, okay, what are the considerations that I should consider when performing this task, given that I am this role and given that this is the task that needs to be provided. So even if the criteria is not necessarily given at the beginning as a document, it will come up with considerations and criteria in itself during the prompt creation process, which is then fed into the multi-agent system.
So have you tried this, or is this in progress?
Yeah, we've tried cases where we didn't necessarily upload like a rubric or more information. And obviously, giving it more of a rubric helps the prompt creation, helps the actual output, the quality of it.
Not so much that. Like I would say the rubric is the prompt, right?
The rubric is part of the context that is fed into the prompt, and the prompt uses to create.
So in this case, yes, the rubric does provide instructions, but the subtasks are actually generated entirely using DISP, which is in the prompt creation step. The only thing it actually takes from the rubric in this context is the word count. So I guess if the rubric doesn't exist, then it might just output something slightly shorter or something something longer. But we have tested this extensively when we don't have a rubric or any instructional files or also any supplementary files to begin with. Oh, wait, one more. Thank you so much.
So hello, my name is Tyler. So this is tailored. We've created a model to give a personalized recommendation for your outfit based on your actual clothes that you can input through an easy and fun to use app. So this is our full team. Unfortunately, no one else could be here today. So yeah, we're gonna start with the introduction, just talk about the motivation, the impact we're gonna have, and also why we chose to go in this direction, as well as the ML model, the choices we made for the architecture, as well as the app design, the UI and UX design choices, and then the future direction for this project. All right, so as students, we all know we don't exactly have the most amount of time in the morning, and we all know that we don't have the greatest time organization skills. So we don't always have the time to create outfits that personally reflect us, as you can see here, or that are even appropriate for the day. So we're trying to streamline a solution that will allow us to not only create outfits for our users based on, again, their personal closet, but also based on their preferences. Now, so just looking at the impact, obviously, the main one is that we can help anyone that needs help with their outfits find an outfit for themselves. But also looking at the bigger scale, we can also take a look at companies that are in clothing and say, if they're trying to figure out which of their outfits they should pair together when putting it in the store or even on their website to make users, again, look at them and be more intrigued by the full outfit or even buy multiple products at once. Now, so unlike our other competitors, we actually allow the user to input their own clothing, which is the biggest thing. It creates a more personalized application. And they're able to firsthand see how their closet can be styled. And also on top of that, they can also add in their own photos of, say, wish list items, which they may or may not want to buy. They're kind of on the fence about, and see how it can be implemented into their closet currently. So yeah, the synergy, we also allow our users to save their possible outfits, log about their possible outfits, and favorite the possible outfits to, again, look back on to inspire future outfits. And so this fosters an environment where users receive valuable style guidance, and companies also gain a strategic platform to elevate their brand visibility and drive sales on users, as they're more likely to purchase items that will, again, more fit into their current closet and preferences. Now for the model, we're going to start with talking about the data set. We're using the Polyvore data set, which contains around 20,000 images, all of single individual garments, which then are part of one overall outfit. Now, each outfit is comprised of an average of 6.5 garments and at a max of 8. And each of these outfits are associated with an amount of views and likes. And using these views and likes is how we'll assess our model quality. Now, for our architecture, we start with the ResNet here, which kind of just takes in, it's pre-trained, takes in a single image of clothing and produces 2048 features. And then using our feed-forward network, we can pass in these features and also a one-hot encoding of the types of clothing that you're inputting, which is actually 3 one-hot encodings. We use gender for male or female, upper or lower body, and then also the individual type of clothing, whether it's a shirt, skirt, dress, etc., which produces the 512 features. And then for the transform encoder, we pass through the 512 features for each garment of an outfit, and a learned outfit token, which then produces the 512 features of, again, the outfit token, which allows us to learn, again, how each garment kind of interacts with one another and produces the general idea of the whole outfit. We then pass these 512 features into the last feed-forward network, which computes the compatibility score, which again is just the prediction of how many likes and views this outfit would receive. Now, the model training so far, again, this is just our first attempt at training, is not the greatest, as we can see here. We still need to clean up the data set a bit, and yeah, at the moment, it's sort of just plateauing at the bottom there. We also need to tune our hyperparameters, as the hyperparameters that we've chosen come from a paper called Attention is All You Need, and clearly it's not working the best for our current needs. Okay, so for the app integration, our idea is that before releasing the app, obviously you want a model that can accurately predict the likes and views of the Polyvore outfits. And upon downloading the app, the user would rate these Polyvore outfits, whether they like them or don't like them. And after this, they can input their own images of their clothing, and then we, again, produce even more outfits based on their clothing, which they rate. Now, using these ratings, we can better fine-tune the model for everyone. Using the polyvore would just be a general, oh, what do people generally like about these more broad outfits, and then fine-tune specifically for the user with how they like the own outfits that we produce. And then after the fine-tuning, we can generate random outfits based on their recommendations and preferences, and push forward the ones with the highest compatibility scores. All right, so why are we using an app? Mainly for user convenience. We obviously want this to be integrated into your daily life, and no one really wants to go on their computer and go to a website and upload some random photo. They'd obviously want it on their phone, where a lot of people do have already photos of their own clothing. And then also for personalization with an app, you can offer personalized outfit recommendations based on the user style, and the level of customization can enhance the user experience and make our service stand out. And also for data collection, it allows you to collect valuable user data such as preferences, feedback, and users usage patterns, which can be used continuously to improve our machine learning model, ensuring that our recommendations stay relevant with, again, the trends of today and also the trends of the user. Now, some of the features, as we said before, for like the rating and just seeing what the user actually likes, we've implemented the swiping feature similar to like say Tinder, allowing you to say which one you like or don't like in a sort of gamified fashion. And again, this allows the users to provide feedback that we can use to, again, more fine-tune to their user preferences. And again, we also have the closet library, which can store your clothes of images that you've taken or say clothes that you want, as well as outfits that have been generated that you have, again, swiped right on and said that you like. And it allows users to look back on their clothes for future inspiration, and also look back on outfits that were created and kind of get a sense of where your fashion direction is heading as well. Now, for the future timeline, we're looking to create the closet camera, which just, instead of moving outside of the app to open your camera and take a photo, it's just all streamlined inside the app. We're also looking to, again, for the ML pipeline outfit builder to come together when the machine learning model is finally trained properly, so it can create outfits based on, again, the clothing items that the user inputs. And also the follow feature, which would be just to create a more social aspect to it, where you can see other people who have similar styles of fashion to yours, and again, draw inspiration from there. And in the idea, in the long run, you can also fine-tune your models based on the other people that you follow, and say, like, if you like their other outfits, it could help the system recommend similar outfits to that. So this is the projection timeline. We've planned to have the model and app design finalized by April, where we can test our model and make sure that it works properly, and then head on to the app integration. Again, just making sure the model can seamlessly integrate, where we can have the data transfer happen swiftly and easily. And then again, just the beta release of the app, assess the functionality, and then monetization if we're gonna make it something real. Thank you so much. Oh, sorry. Yes.
Yeah, a really great presentation. My question is, how do you make sure that your app, this fashion bot, isn't biased towards some individuals who might have more unique or culturally different preferences for outfits? So I know that you mentioned that there's some user customization, so I can like input my own pieces. But does that mean that if my outfit preferences are very different from like Western norms, it's going to take a long, long time for the app to like learn my preferences versus someone else?
Great question. So the initial data set, again, is very broad, but also when you're looking at the actual, I guess, your actual clothing, it's not going to draw, like, it can only produce outfits based on your actual clothing, which I think helps negate that. And the idea is that, again, I'm not sure how long it would take, but assuming that the model, again, is working properly, and you take in, again, the swiping right and left and actually seeing which ones you personally like, it should pick up on it quickly. And again, it's not going to focus on, say, Western clothing items if your items are not in the same culture, because it can't push forward clothing items that you don't own.
Hey, thanks for the presentation. Can you tell me a little bit about the data that you have collected so far that you're fine-tuning on?
Well, we haven't started fine-tuning yet because obviously the model hasn't fully been trained yet. But the data, again, is... sorry, let me just go back. It will just be the actual item of clothing put onto like a white background. And so the outfit, so if you see like the green highlighted ones, all of those come from one single outfit.
And that has the views and likes.
And so the overall outfit has the views and likes, and the individual items have price, and that's about it, but we don't really worry too much.
You
about
are
price.
trying to predict the views and likes, if I understand.
Exactly. So we'll take in, say, all of the green highlighted ones, and then pass it to the transformer encoder to get the overall idea of the outfit, and then produce through the last feed-forward network the likes and views of the outfit as a whole.
I see. So you have the data for the individual items, but you don't have the data for the combined, and you're trying to predict the combined.
Sorry, we do have it for the combined.
Oh, you have it for the combined.
That's the baseline we're going to use to determine error.
All right. Cool. Thank you. So I would just quickly suggest trying just zero shot.
Zero shot.
Yeah, so just like plug it into the OpenAI API, see what happens. I think it might be better than fine tuning.
Oh, okay.
I would also just like suggest, like if it doesn't work with zero shot, I would try rather, because like attention is all you need is really like language translation. So it's not surprising that those parameters with a very kind of custom architecture would not converge. I would just try to zero shot, few shot, and like fine tune like the OpenAI API or something like that.
Okay, thank you.
Yeah.
All right, thank you so much.
Okay, bet.
Okay. Hello, everyone. We are the RNA folding team, and we'll be presenting today, the UTMIST RNA folding project that we've got together. So, since the turn of the 21st century, biological data has grown exponentially to the point that we now have terabytes upon terabytes of biological data that is in a public database that is just there for open mining. To the point that this year, the biological Nobel Prize, the Nobel Prize in chemistry, was given to AlphaFold, a end-to-end deep learning pipeline that predicts the protein structure. Now, going off of its success, we are now essentially asking the question, where is the AlphaFold for RNA? So that is sort of the premise of RNA folding and what we're going to be talking to you about.
So we are focusing on RNA folding. So a brief introduction of RNA. So this is a special macromolecule in our body that goes in between the DNA and the protein. So we all know from biology that the central dogma kind of describe the process in which your entire kind of transcription process works. Your DNA in your nucleus is being transcribed into RNA, mRNA sends to cytoplasm, and then it's being translated into a protein. So there has been a lot of studies on DNA in like genetics. There's a lot of study in protein, which is kind of the functional unit and kind of how we really have our like biological function works. But the problem is RNA. So there is a lack of data regarding RNA. It has that extra hydroxide, which means it's less stable than a lot of other biochemical macromolecules in our body. So what we really want to know is how we can actually use RNA, because the size is really helpful in terms of like a lot of precision medicine. It is helpful in terms of like a lot of like virology studies and things like that. So in biology, basically, the structure really defines your function. So how we, like what we really want to know is how the structure of a RNA, which we describe as a sequence, is, you know, kind of like a string and then it folds into a ball. But how does it actually fold? Like, how can we predict the 3D structure, like the function, the structure, so that we can determine the function? So in the past, for the past century, 19th, 20th, 21st century, kind of the classic way of doing that is through chemistry, X-ray crystallography. We have NMR, so nuclear resonance, magnetic resonance, and things like that, to use experimental features to kind of predict the molecular 3D structure. The problem with that is that it's very expensive and it's very time consuming. So in the past, like to determine one kind of structure of an RNA, not only do you have to kind of freeze it, X-ray crystallography, but it's really unstable. So it's really hard to maintain like a really accurate 3D structure. So what ended up happening is there is like only around like 2,000 RNA structures, while protein we have like 400 millions. So basically the problem with that we have is how can we actually like use kind of limited data to construct a model that is very helpful and very useful for the scientific community in general. So obviously we are not the only people that is concerned about this problem. There are a lot of different competitions. So Cas15, well 16 now, is kind of this competition that it used to focus on like protein structure prediction, but then after like, you know, AlphaFold came out, they're like, it's okay, now we move on to RNA. So they are used to predict RNA. RiboNanzaNet, so RiboNanza was a competition hosted by Stanford on Kaggle that helps to determine RNA folding structures. And then RNA Puzzle, this was a French-Chinese they also have a competition to help with structure predictions. And right now, like all of these are using AI. So basically, our question is, when will RNA have its AlphaFold moment? And we hope that it's soon. So I'll pass it to.
Yeah, so going off of that, the question again was, when will RNA have its moment? So what we are actually trying to do is advance the state-of-the-art, you know, push the ball forward, and using novel methods, try and develop the state-of-the-art 3D prediction method. So our main approach is essentially two-pronged. First, let me just talk about like what we're doing. Now, RNA is a very vast and diverse molecule in the body. But for us, we are starting on ribozymes as a starting point, because there are like tens of different classes, and we want to focus on one, make the best out of it, and then like go on to different molecules. So ribozymes are essentially a class of RNA molecules that are very diverse. They have some interesting properties, which I can go in later. Now, what we're actually going to be doing is, as I mentioned before, there's a huge public database which we have mined to generate like hundreds of thousands of new sequences to actually feed into our language model. Now, this database is 50 petabases, 36 petabytes of just like public open access data. And it's a very vast resource for us. And then finally, training on both sequences and structures. As you mentioned, the structure database is very, very limited. For us, after subsetting it to like very high quality structures, there are just 200 structures, like, very easy to overfit on a model. So, which is why we're supplementing it with this new database that we've also generated. Now, going into ribozymes. Ribozymes is what we're essentially focusing on for our project this year. And there are two reasons we focus on this. One, for its diversity, and two, for its biochemical nature. It is very, very diverse. This is just one example of a structure. It comes in like many different shapes and sizes. And also for its biochemical nature. These are also called the molecular scissors of the body. And it's actually surprising. A fun fact is that ribosomes that make proteins in our body are actually RNA molecules, like these specifically. So stuff that makes proteins are actually RNA. And it's really cool that after scientists figure out their structure, they can now they understand how the body works and how proteins work better. Now, going into the sequence read archive, which is like one of our main prongs of like the data that we are actually mining. The sequence read archive is currently the largest publicly available collection of sequence data, over 50 petabases, which has exponentially grown since the early 2000s. And a really fun fact, again, is that there are more than 27 million libraries, and the cost of sequencing has decreased faster than Moore's law. In the 2000s, it was about 100 million to sequence one genome. Now it's come down to about $1,000. This has shown how fast biological data has been growing, and all of this data is now publicly available, which we are now using to do so many different, which the public is using to generate so much more insights. So how are we actually doing this? Well, as I mentioned before, mining it to find ribozymes. Now, as a very quick overview, I generated a couple of different models to capture the diversity of ribozymes, and then just querying it over the entire sequence read archive to generate a bunch of new structures. Sorry, to generate a bunch of to get a bunch of new sequences. And these sequences will then go into our ML pipeline.
Awesome. So yes, so basically our ML pipeline, it's kind of tailored towards the fact that we don't have that much structured sequences, and so there are kind of a few key components for this. So the end goal of our project would be to predict a tertiary sequence, which is like kind of the ball, from a primary sequence, which is just like code like AGCU. So how it actually works is that you first have so the two middle components plus the row fold they are help to predict a secondary structure. So secondary structure is kind of like you have like your base pairing information, but you don't actually have like a 3D structure. So you have the location, but not really like the diffuse like kind of the actual 3D structure. So let me just go over like kind of the 3D structure first, because this part is kind of easier, because once we get a secondary structure, how we get from there to a tertiary structure, which Flora is working on, could be either through diffusion model, or it could be through TR Rosetta fold, which is something David Baker, he just won the Nobel Prize in Chemistry for AlphaFold. So the tertiary structure is like kind of okay. So how we want to go from primary to secondary structure though is actually through transformers. So we use RNA-FM, which is RNA foundational model, and a pre-trained RabbleNanza model to generate two different types of embedding that kind of encodes for different information. So the RNA foundational model mostly cares about like the different structural kind of relationships with like a multi-headed tension. And then for the RiboNanza net, which is so that net is actually distilled from the top performing model for the Kaggle competition RiboNanza. So that model is really good with chemical mapping formation. So these two different foundational pre-trained models, they encode for different information, and we can get two pairs of different embeddings through them. And then from there, we will there's also a third kind of key pair, which is multiple sequence alignment, MSA, that also encodes for like kind of evolutionary information that encodes for how like base pairs happens. So using these kind of three different types of embedding, we hope to put it into row fold plus. This is kind of the current state of the art model for RNA folding. You can see the middle part, like they have MSA and the embedding from RNA-FM, but we're adding another layer to that in order to create something that we can feed later into the model and help with having our secondary structure prediction. So this is kind of how we are doing our row fold. And because we Parag just mentioned like lack of a sequence data, we will use not only just the sequence data, but also like evolutionary, also chemical mapping, which gained from experimental data to kind of capture the diversity and nuances in the data that we're using to like prevent overfitting in general.
Yeah, so currently we will be training the final pipeline that we have. And based on this, our future plans are to essentially expand out to other RNA classes, like other RNA molecules, tRNAs, riboswitches, et cetera. There are like tons of different classes that we can focus on. And the other thing that we want to do is, as we mentioned before, there's a very limited number of structured data. So this is essentially our purest data source of experimentally generated structures. And this is like the ground truth. Now, we want to essentially augment this these 3D structures with like a bunch of different methods, like noising it, adding in like different, changing the MSA, changing the sequences, all the different methods to essentially generate more variations of that our ground truth to help with the training process. And that essentially is encompassing our entire project. We are planning on, we are planning on creating an end-to-end pipeline by fine-tuning our language model, feed it into a already published and state-of-the-art transformer end-to-end deep learning model, fine-tuning all the different parts of it, and then we generated more sequence data, and I'd like to thank our entire team, plus Professor Artem Babian for giving us the compute for these large-scale data mining and training processes, and our mentor Andrew from Deep Genomics. So yeah, thank you. Yes, any questions?
Hi, great presentation. I was thinking, do you have any concerns with augmenting the targets in terms of structure? Because it's not really a classification problem, right? If you change a few genome bits, wouldn't that modify the structure completely?
You're exactly right. So that's why that's on our future plan of like what we want to do. But a lot of the structure was made off a MSA. So it has essentially a thing of like an n by m matrix of like a bunch of sequences with the top row being like the main sequence. Now, what an MSA essentially gives you is you want to see the conservation of you want to see like essentially the patterns, like which parts of the sequence are more conserved. Like you want to see like which ones are the most important parts of the RNA sequence. Now, if you can try and like noise up or like, add in noise into the other less conserved parts, which are kind of less relevant, then that can help augment the data, which is then feeding into the 3D structure. Yes, obviously, like it is very hard to change the exact structure because we don't know what effect it would be. But by changing the sequence data and by adding in like a bit of noise into the like multiple sequence alignment, that can help create more training data for us.
Right. So in this case, it'll pick up on the important parts in the RNA sequence.
Exactly. Yes.
Noise.
Hey, thanks for the presentation. I'm not sure if you had that slide, but could you take me through the current input-output kind of data set, as well as if you're planning to change it in the future?
This one?
So I guess I'm more, or maybe you can talk me through it. So like, what's the input, what's the output in your current system?
So the input is very simple. We have a sequence that comes from an MSA. An MSA is an n by n matrix, as described before, that represents the evolutionary path of the RNA. So we have the first row, which represents the most recent RNA, and then we have all of its evolutionary path. So it becomes a matrix. Then, as you can see, there are different parts to the model. Let's focus on the right. We have row fold. We have three parts. We have RNA-FM, row former, and structure module. Okay, the RNA-FM is actually a separate paper that came out. It's a language model. So the goal of this language model is given an input to predict the next base pair within the sequence or whatever the token is. In this case, they have a base pair resolution. So if we look into RNA-FM, it's just a classic let's say it's a sequence model, so it's similar to how something like an LLM would work, but for sequences instead. So the input in that case.
Yeah, I'm sorry to interrupt you. So I'm kind of just in the interest of time. So I'm more interested in like so the output.
Yeah.
To my understanding is the next base or something.
Yeah. So given the input sequence, RNA-FM. So row former takes in the attention maps of the language model, so which gives the relationship between the different input sequence. Then given the attention map, the row former and the structure module, which are recycled 10 times, then output the secondary and the tertiary structure. So RNA-FM is already capable, based on the base initial original sequence, to base pair to return a secondary structure. But our goal is to essentially form a tertiary structure. So a tertiary structure is a bit more complex than a secondary structure. So it contains all of the full folding pattern, and that's what is harder to do. Does that encompass your answer?
Yeah, I think so.
Great.
Thank you. Can I ask one more?
Yes, of course.
So do you have the performance on this So I guess kind of this would be kind of accuracy or cross entropy or something.
So for the RNA-FM, which are currently first fine-tuning based on the ribozyme data, yes, it would be based on something like perplexity, which is what we're using for. So it's basically how similar the data is.
Yeah. So I'm asking more like, so have you run this, or is this in progress, or?
So currently we focused on the data mining process, which
Okay.
yeah.
Okay. Thanks. Yeah, I got it. Yeah. Okay. Thank you.
Yeah, like we've set up the process like literally a couple of days ago. Like we finished the data mining step, and now like we just have to run the RNA, like fine tune it.
Because the fine tuning process can run simultaneously, but we can't really get an accuracy report
Sure.
until we have the data that we.
All right, who's ready? Okay, we're only going to start when everyone quiets down. Okay, that looks important. So, okay, are we ready? Let's do introductions. My name is Sean.
I'm Ashish.
I'm Tana.
I'm Hamad.
And
I'm Anoop.
uh,
All right. We are AI warehouse team. Uh, yeah, there we go. Uh, let's go around the introduction actually. Yeah, so I don't know if it's recording. Yeah, so our team essentially is building a platform for AI Warehouse, which is a YouTube channel with over like 600,000 subscribers. Yeah, so we're working with them in order to create a platform where they can essentially expand on on our platform and make YouTube videos for their YouTube channel. Yeah, and oh, sorry, yeah, my bad. Yeah, essentially, our project is a battle simulator where we use the NEAT algorithm, Euro Evolutionary Augmented Topologies, yeah, to pit Albert, which is essentially the innocent good guy, versus Kai, who's up there with the sword. Yeah. um, yeah. Go ahead.
all right, so what is NEAT? NEAT is a technology that was developed at U Texas, which uses genetic algorithms to change the structure of neural networks instead of like traditional neural networks where there's like a bunch of neurons. And these and you use crossover speciation and mutation in order to learn and adapt those agents over time. What essentially you're doing is that each there's a bunch of genomes, and each of those genomes have different species which they are divided into. And within each generation, some of these species are preserved so that, and those ones are randomly added connections and added mutations, and we try to put them in a fitness function and see which performs in the best manner possible. Preserve those species, delete the ones that are gone over each generation, and even because of this randomness, we come to results that are astonishing, even in very, very small neural networks.
Okay, yeah. No, why is NEAT so significant part of our algorithm? Because NEAT essentially follows how real life evolution works. Instead of like backpropagation, which essentially has a direct target towards like the best optimum solution, the way NEAT operates is just sending in like 100, 200 agents and then just letting them figure out purely randomly. We just keep the best of the best, and then we add slight mutations. And this helps us to essentially model real life scenarios. So like we can model how does violence come about? How does the altruism come about? So yeah. You want to talk design team? Yeah.
Okay, we had 3 teams. I was part of the design team. Mohammed was part of the Unity team. And we had a few people on the algorithms team, but they're not here today. But anyways, I was part of the design team. And as such, me and my team designed assets such as Albert, which is the orange dude, and Kai, who's purple and a bit blue, but he's a very angry person, so his color doesn't really reflect him. The thing with designs is we are working for AI Warehouse, so we need to embody their identity when working with their designs. So one of the emblematic things about AI Warehouse is that Albert is a very innocent and he's a bit submissive. So you can see in his eyes, they're a bit cross-eyed, which was a specific design choice. And essentially, we just followed design principles in making sure that our designs were uniform with the AI Warehouse brand.
Okay, algorithm. So the main algorithm part of the neat algorithm itself was designed by the algorithm team. And based on AI Warehouse's demands, they wanted an algorithm that they could use as a package and insert wherever possible in all of their other projects, right? So we recreated the entire algorithm in C# and modified it in manners that they could use it in multiple projects. And it is working out well based on the Unity team as well, that they are very easily able to integrate the algorithm into their program. And the idea is that to make the code so modular that they can take out certain aspects of that code and put that into their existing database and create even better outputs and create even better performing models based on different config files. And by changing different configurations, they should be able to create a deterministic system where they get some particular output that they desire. Like, for example, if they want them to have a war, then they should be able to modify the config files so that they have even more evolution in those aspects, and they reach the stage of swords and shields sooner, and they get a gold sword sooner than they should be, and like those kind of things, and like making sure that that is a possibility in the system, and we are able to get those outputs consistently. You were talking about Unity?
The Unity team is essentially the glue that brings together the design team and the algorithms team. In the Unity team, we actually implement these scenarios. We put in certain like, oh, what if Albert's lived in this site and Kai's lived in this site, and we had a resource disparity. Like this site has much more resources. So what happens to the generations? Well, yeah. The Unity team has to be incredibly modular in the way, just like their teams. It has to be modular because when AI Warehouse essentially takes over the project, they have to add in, they want to add in more features. They want to create new maps. So we've added, like, we've technically used this thing called like a 2.5D perspective, which looks like 3D, but is just a fake 2D. Yeah. Yeah. You want me to do this? Okay. So we have 3 research questions. The first one I already talked about, which is the resource disparity. The second one is like herd mentality. If you see some creatures like cows and stuff, they always move in herds. Why is that? These are some of the questions that we can, like, because of the way NEAT works, we can test this out, and we can see why would they form herds? What is the specific conditions that they start forming herds? And the third one is there an evolutionary advantage to violence? So is a resource disparity, does resource disparity actually cause violence? So these are the kind of questions we want to map out.
So in terms of goals, the first one is, again, because it's a YouTube channel, to develop an visually engaging video where all the elements are made in the manner that they prefer it, and they can use it in multiple instances in multiple videos, right? And the other thing is to figure out what kind of strategies do these models use when they go against each other. So we will have 2 maps, right? So we'll have Albers on one side, Kais on one side, and we want to see what strategies each of those sides, based on the resources they develop, to be able to act and defeat their opponent, essentially. Right? And create a toolkit that can be used for other evolutions, as well as encourage collaboration among researchers and game developers by the research paper we'll be publishing at the end of this project.
Yeah. I think we covered how through all this speaking, but essentially, how NEAT algorithm, the reason we pick NEAT algorithm is because it tries to emulate how real-life evolution works. Unity simulation environment, the reason we picked Unity is because AI Warehouse primarily works with Unity, so we just decided to keep it simpler for them, and we decided to use Unity. Survival of the fittest is essentially how evolution works. The best of the best survive, the rest get discarded. Data collection and visualization. So we're currently in the process of data collection and visualization, where we are creating scenarios for each of the research questions, and we'll collect data like the population density, population, and how far they spread out. So yeah, next.
Yeah. So the outcomes we have already established within less than 5 agents that within this population it's working out, and we are able to simulate things like the XOR function and the sine function, and they are working out way too well. We are able to get the sine function running in under 50 generations with less than 4 to 5 layers of the neural network, and then model and scalable toolkit that we have mentioned before. Testing and scaling goals. So we are trying to run over 100 agents on each side of the battlefield and try to see what kind of battle scenarios we can generate. And the expected result should be done by early March. We are already in the integration process between the algorithm and the algorithm team and the Unity team, and we have been able to get the integration running and mutation happening. So hopefully by early March, we should have a really cool project ready.
Yeah, this is just a gallery. Uh, sorry?
No.
You were saying. Yeah, we didn't really have pictures of just our team, so we have the Lovelytics team as well with us. But if you see, the AI warehouse teams has the glasses. uh, you can. This is 2.5D. It's literally just a picture of 2D, but it looks almost 3D. You can like see it in some Pokemon games. Yeah, we have some boards of like our work. That visualization over there is our neat algorithm learning sine function within like 20 generations. So the 20 generations is insane. So yeah. Thank you. Any questions?
All right. Thank you, everyone. Any questions from the judges, from the crowd? Yes, sir.
What are some examples of like your state variables on how you encode submissiveness into an agent, and maybe like what's the action space? What are they allowed to do, and how are they rewarded?
Absolutely. This sounds like a question for the algorithms team.
It's a Unity team. Yeah. So there's no exact like submissiveness kind of thing that we're really parameterizing. It's more like we just want to test out. They're essentially the same character. Even in their videos, we don't really give them that much. In AI warehouses videos, they don't really make them that different. So they're essentially the same character. We've just given them a cute little personality. Yeah.
Now, what are they allowed to do in this battlefield? Like, what are the actions?
Okay, so yeah, I don't think we covered that, but yeah, essentially they have like a sword which they can attack. They have a bow which they can shoot. They also have like rocks, trees, and fruit. So each of these help increase their stats, like the attack damage, attack speed, like their running speed. So like we have like these stats in video games.
So to add on to that, like the map will be asynchronous. So one side will have more water-based elements, one side will have more rock-based elements. So like the Kai side will have more rock-based elements. So essentially, we'll be able to see how having different resources will affect different stats. And essentially, in the end, they will have to cross a river, and they will have to face the other side if they're out of resources or something. So and
Is the goal just to kill off the other side and stay alive?
the goal is to stay alive. If they decide that in the end that it's better to just stay on your own side and be alive for longer, then that is also a possibility. So like that's something we are gonna see. And because the system is deterministic, we'll be able to simulate either of those environments.
Okay. Could you please speak again to like the real world impact of this tool? Is it for, I'm not too familiar with AI Warehouse, the YouTube channel. Is it for creativity? Is it for fun? Is it for entertainment? Or is it for education?
So the AI warehouse channel is mostly for entertainment and education. It's not like a direct like, oh, this is exactly why. It's more like to gain an insight into like how it possibly could happen.
Okay. I think you, sorry, you wanted to add something?
Yeah, so to add on to that, essentially, what their entire goal, like the channel's goal, is that they do not see enough RL content on YouTube, like reinforcement learning content on YouTube.
Yeah.
So they want to make real reinforcement learning fun for people to enter. So they sometimes in the videos they tell that, okay, we are using this technology to do this. So like to inspire, like and bring some more interest into the field, essentially.
Okay. I think you mentioned on one of your slides that there's like a potential for researchers to maybe use this. I guess like what do you need to add in your implementation or your testing or validation to make sure that this sort of tool would be valuable to like a research context?
So there's the one aspect of that is that an aspect of Neat that was developed called real-time Neat did not really go far. Like the only version I could find of it was in C++, and like no one was essentially using it. So we are trying to emulate that with Unity as well, so that this will be really good for researchers, because in a real-time environment, how can you simulate generations, like being at the same time? That's how it's in real life. Like you have your parents, you have a child, and you have like different generations co-living together. So we're trying to like re-simulate that environment using this algorithm. And in that regard, it's going to be really, really useful for researchers who are in game design to see, and in game, and even in aspects like game theory, where it's important to see how different like statistics can lead to different outcomes essentially. So like in when you talk about it in game theory, it's more like, oh, this thing happened first and this thing happened second. So what's gonna, like there's like a strategy map, right? So like these kind of strategy maps can be made at random based on the algorithm essentially.
Okay, thank you. Okay. Thank you guys.
Thank you. Thank you.
So next on stage, we're going to be having the chatbot team. Sneha, white sweater.
Good morning, everyone. I think it's still morning right now because it's 11:58. But we are the AI chatbot team here at UTMIST, and our project is called the AI Navigator. Has anyone here ever been confused about what's going on at UTMIST, like the current projects or like what's actually happening? Because that's where we come in. We are a chatbot team that is building a chatbot that not only answers the frequently asked questions people have about the team, but we're also a ML or AI learning tool that recommends people um, ML related resources that is tailored to your own specific needs.
Moving on to motivation. Last year, while working as a marketing director at UTMIS, I noticed several like inefficiencies in how our teams handle student inquiries on social media platforms such as Instagram. The marketing team was really great at promoting events and managing outreach, but when it came to technical questions such as how to get started with AI or ML, what kind of roles can I apply for based on my skill sets, and how to improve specific expertise, they often had to redirect those questions to VPs or like technical members at UTMIST. This back and forth process is sometimes really chaotic and time consuming. Beyond this internal challenge, there's also a broader problem with how people seek guidance in AI and ML learning. You might have noticed that even powerful tools like Google Search or ChatGPT often provides generic and also surface level answers. If you ask, how do I learn machine learning, like shown on the screen, Google Search just throw a bunch of conferences, Coursera courses, or like textbook recommendation to you without real personalization. Those systems suggest resources kind of blindly without for first understanding your background, preference, or constraints.
So the purpose of our project is divided into three distinct parts. The first part is the original goal for our project, which is to design a chatbot that supports UTMIST social media accounts and answers questions that people might have about the club. And the second one is to provide a resource to help people learn about ML and AI and to provide a personalized recommendation. And the third one is more of an internal goal, which is to provide a platform for people to learn how to employ core AI and ML concepts that you might learn in courses here at U of T. And now we'll move on to the general overview. So the overview of our model looks like this. Last year when we started this project, we were originally only designing a frequently asked questions like chatbot that answers your questions about UTMIST, which is essentially we have a embedded vector database that is all of the UTMIST internal data, as well as the we also scrape Instagram feeds and other social media accounts, and we pass that into a RAG system, and then it essentially retrieves the relevant data that's relevant to the user query, and essentially spits out an output. However, for the second part of our project, we wanted to design a conversational recommender system, which Adeline here will explain.
So for the conrec system, the pipeline starts with processing user inputs with intent classification, which determines whether the user is inquiring about a topic, providing preference, accepting a recommendation, or something else. Simultaneously, constraints classification identifies factors such as device compatibility, time availability, skill level of the user, and etc. Those constraints are categorized as hard constraints, which must be satisfied, or soft constraints, which are ideal but also flexible. Next, the action recommender evaluates whether there's enough information to provide a meaningful response. If not, the chatbot asks follow-up questions to inquire more information, and if otherwise, it proceeds to information retrieval, fetching the most relevant data based on the user's unique profile.
All right, so I'll walk through our approach for classifying user intents and constraints. Our objective is basically we want to classify text prompt into multiple intent and constraint categories. We have in total 6 possible user intents showing on the slide, and they are provide preference, accept recommendation, reject recommendation, inquire resources, club-related inquiries, or just in general short answer inquiries. And we use a multi-hot encoder vector to represent the label. An example could be a user asks, what event can I participate at UTMIST? And I'm a beginner and would like some beginner-friendly events. So in this example, the label will be 100, 1 for provide preference, 1 for inquiry resources, and 0 for other categories. For constraint, we have 2 possible categories, which are soft versus hard constraints. In the training data, they are represented using 1 and 2, and under the categories on the slides, you can see we also identify many types of constraints. An example for constraint could be like the user says, I only speak English, then the constraint will be 2, indicating it's a hard constraint, then the chatbot will take that in mind and provide only English-related resources. And data for both tasks are generated using tools like Hugging Face's synthetic data generator and also ChatGPT prompts. In terms of model building, we built 2 classifier models, one for each task using a semi-supervised approach. It was actually inspired by a research paper that applied semi-supervised learning to image labeling, but we adapted the idea to our text classification task because we want to leverage large amount of unlabeled data to improve the model performance. And here's a process. Before everything, we first separate our data into labeled and unlabeled. Phase 1 is that we train 2 independent Roberta-based classifiers on our label data. Then phase 2, we use both trained classifiers to pseudo-label a large amount of unlabeled data. And we only select samples where both models actually agree with each other so that we can increase the confidence level for the pseudo-labels. And finally, we combine the original labeled data with the pseudo-labeled data and train a third and final classifier on the full data set. So this expanded training set improves the overall performance of the models. So in summary, we basically leveraged a semi-supervised strategy to build both models for intent and constraint classification.
Okay, so the next step in our pipeline is something called action classification. And essentially, what this part of the pipeline is asking is if the JSON state, so essentially the user query, the hard and soft constraints, and the intent classification, if that's even enough information to provide a high quality recommendation. And so this task is a pretty simple task. It's just a classification task, but it's pretty crucial into the pipeline because it's essentially what makes our recommendation system conversational. It essentially acts as a feedback loop where if a user enters a prompt and the pipeline determines that that prompt is too vague, it'll prompt the user itself and ask for more information. And so it basically makes it more human-like and not really like static. And so again, if it's we have two classifications. It's either request more information or generate recommendation. So assuming the classification is generate recommendation, i.e. the given data from the user is good enough, that's where sort of information retrieval comes into play. So IR is basically a branch of machine learning. It's essentially just concerned with if you have a query, you sort of just search a corpus of documents. In this case, the corpus is just a collection of machine learning resources. And it sort of ranks them from most relevant to least relevant in terms of the given query. So traditionally, IR was sort of sparse, as in it was sort of like traditional methods like TF IDF and BM25. I believe Google still uses it, but they have limitations in that they can't really that those sparse methods can't capture human semantics, i.e., how humans actually speak, and so that's where sort of foundational models and more dense methods like LLMs come in. They are able to capture how humans speak, which is really powerful in our case as we do have a conversational system. Um,
I'll dive deeper into like how we actually fetch the relevant resources. So first of all, we need to store all the ML resources somewhere, like in a database. But we cannot just store them directly. We need to encode them into vectors of numbers. These are called embeddings, and these are easier for machine learning models to work with. We can use an ML model called dense encoder to compute these encodings for us. And then we can store these embeddings into a vector database like Quadrant. Once we have all of these resources in a database, the embeddings in a database, then we can use the query to perform a cosine similarity search to get all the relevant resources.
So here it's just sort of a mock sort of conversation between a user and the chatbot. As you can see, the first prompt, the user is asking how to create a chatbot, but it's a bit vague in terms of the user's background. We don't really know much about the user, and so the sort of chatbot recognizes this and reprompts the user for that information. And then they reply with "I'm a beginner," which gives some information, but again, it's still vague. And so that feedback loop reiterates and asks for more information. And then finally, the user is a lot more specific. They even answer with their system, sort of what system they have. And then from there, the chatbot is like sort of satisfied with those pieces of information, and it's comfortable giving an actual recommendation. Um, yeah.
So what's next? So what's next for our project? So right now, as you know, a lot of the big problems with chatbot projects is the hallucinations and optimizations with prompts and the models that are built into that are integrated into the project. So that's one thing that we're actively working on. And then the second thing is the implementation integration with different social media accounts. Because right now we're working in Discord because it's the easiest and most open um, developer portal. And the third thing that we're actually working on is like live updates and how to update information so that it matches real world scenarios. And that's all. And then we want to thank Professor Scott Sander for giving us this idea on the conversational recommender system. And that's all for our presentation, and we're open to any questions. It's not updated.
Hey, thanks for the presentation. I guess, so what's the stage in terms of using the RAG? Because that seems really key. The dialogue that you've shown, you could get from ChatGPT, right?
Um,
It takes the JSON state and it sort of converts all of those like pieces of information into a natural language prompt and then prompts GPT.
I mean, I guess what
Or
I'm asking
rather,
is,
yes, sir.
so in term, so you do have have you tested to what extent the RAG actually helps? Because kind of, I guess, kind of the dialogue that you've shown on the slide, right? That's very generic. It's not.
Yeah, we actually we did have a demo, but I don't think the slides.
Can you maybe just describe kind of things that you're able to retrieve, stuff like that?
Yeah.
Yeah. So we actually were supposed to have a screenshot in here, but I don't think the slides updated on the actual conversation. But essentially, what our bot is able to do is when you prompt it, it essentially saves everyone's like the chat history log, as well as the constraints and the intents that are already classified in the chat history, for instance. And then when you're retrieving it, it not only retrieves from the embedded vector database about UTMIS internal data, but also on our ML resources that we've also fed in there as well. So I don't know if that answers your question, but essentially, if there isn't enough data, it also prompts the user to essentially it will also request more information from the user.
Just one last follow-up, and I'll give up the mic. So I guess what I'm looking for is an example of something that you've seen in the system where ChatGPT would not be able to answer it, but you're able to get a specific answer that's, I guess, UTMIST specific.
Oh,
So
yeah, for sure. Yeah, for our RAG system, we can actually see what is retrieving specifically from the vector database. And when we tested it earlier this morning, for instance, we sent in a prompt on if I'm a beginner learning about ML, what can and I'm a U of T student, what can I pull? What can I do at U of T? And it will be able to pull, for instance, the like hackathons, for example. It was like pulling from like Hack the Mist, which is coming up. It will also pull from like different ML projects that are going on as well.
Great presentation, everyone. My question would be mostly about making this solution more scalable. So I understand right now you are using Discord, right? Have you thought about using cloud-based services like AWS Lex, for example, or such products?
So in terms of Discord, like the chatbot interface is on Discord, but when we're deploying the models, we will have to use a cloud service. We haven't gotten that far yet. It's sort of just running locally on our machines, but yeah, the vector database we're using, Qdrant, is a cloud service. So, and then to actually deploy the model, we probably have to rent out a server or something, because the Discord bot will have to be like running continuously. So we'll probably have a server.
Yeah, great presentation. I had a question about sort of, I guess, like the implementation considerations and potential consequences of this. So, could you maybe like, have you thought about implementing this in UTMIST, for example? I understand that there are probably like benefits and efficiency that'll arise from using a chatbot like this, but isn't there also benefits of like, yeah, maybe asking someone a question that's been answered before isn't efficient, but doesn't that build small talk? Doesn't that build relationships like within the team? Could you maybe like again justify the need for this and how you're gonna, and maybe some potential like consequences of implementing a tool like this?
Yeah, I can give that question a go. So the chatbot isn't meant to replace, like, for example, the marketing team at UTMIS. It's more of just like a first point of contact. If you're very new to the club, or you're like a second year, third, or first year undergrad student, where you don't really have much experience. I know personally, like I was pretty like scared to go up to upper years. So if that's the case, the chatbot is a great sort of first point of contact for that. Anything to add?
Yeah, and something else in our system that was not outlined in the project, it was in the classified recommender action. There was also a classification where it goes into like, it will actually refer you to someone to talk to if the question cannot be answered quickly by the chatbot. So it's more of a, yeah, like a first point of contact, like Osman said. Thank you so much, everyone.
Thank you.
So now can the QDifuse team come to the stage?
All right, what? All right. Let's wait for people to settle. All right, hi guys. So, okay. So let's begin here. So just before everything, I go for our projects. I just want to introduce myself. So I'm Jeffrey. I'm a second year engineering science student.
I'm Michael. I'm a first year engineering science student.
So there should be a lot more team members here, but unfortunately, due to time constraint, they're not here. So we will be representing our team to describe to you guys what projects we have been doing. So the name of our project is called QDiffuse, and by names you can tell it's a connection between quantums and also diffusion models.
And essentially, what we're trying to do is to map the connection between quantum technology, aka quantum annealers, to the diffusion model to see how well we can improve the performance. So maybe first we can go over some basic context of what we're doing here. So the core of our model is an RBM, restricted Boltzmann machine. So the way I believe people here should be familiar with this topic, but you can understand it as what a Boltzmann machine does is to find the alignment of all the nodes with minimum energy, which is a simulation to a physical world. And this characteristic of having the energy function is what brings the connection between quantum annealer and the restricted Boltzmann machine. And once it reaches the minimum energy, it will help us to try, let's say, we feed into an image, it can help us to denoise, will help us to do classifications of the image accurately. So knowing all those information, oops, sorry. So now the way how we're supposed to train this restricted Boltzmann machine is through the way called sampling. So let's say you have a probability distribution of an image, and that probability distribution tells that on this pixel it should be like it should be a value of 1 or it should be a value of 0. It should be light up or it should be like a dark color. And with that probability distribution, we sample the image many times, and you arbitrarily pick whether that thing is 1 or 0 on a pixel based on the distribution we have. And this sampling process can be shown on the average products over there from data and also from model. By model, it means that it's just we just leave the models to hallucinate itself. It's just adjust the weight and then just keep generating new images. And from data is something we compare with the actual ground truth images. All right. So how do we map the connection between quantum technology and also the RBM we have here? So quantum annealer, how you can understand it is that there's an array of atoms, so which you see on the red dots and the black dots. And for each of the atoms, that represents a node in the RBM. And all the connection or the entanglements between each of the atoms represents the weight. So how much they entangle, how much they interfere and influence each other becomes the weight between each of the nodes in the RBM, which you can see the connection we draw over there. And this quantum annealer actually follows similar logic as RBM. It's trying to find the minimum energy state for the combinations of all the atoms, such that we can just find an optimization method. And also, why we're using quantum annealer at this point is that there are some literatures already shown that using quantum annealer to do the sampling process, which is the process we use to train the model, can like bring better quality and higher efficiency, because quantum annealer functions at a scale of milliseconds. Meanwhile, the classical model functions a lot longer than that. And yeah, the reason why this quantum supremacy exists is because of the quantum tunneling property of the particle itself. So classically, if we do by adiabatic evolution to find the minimum energy of an RBM, then the particle will slowly approach the minimum energy state. However, for quantum annealer, they could tunnel through the barrier to find the minimum energy, and that's how it achieved much faster rate of converging compared to classical RBM. So now I will give it to Michael. He'll explain the rest of the content.
So diffusion models. So essentially, this is what we're trying. This is the model we're trying to improve using quantum annealing, specifically quantum RBMs. So the way the diffusion model works, this is the training stage. So we take in a clean image, so like the dog on the very top left, and we slowly corrupt it. And we do this using a deterministic process, like a Markov chain. And so we add noise until we get like a Gaussian distribution. Every pixel is like a Gaussian distribution, and the joint distribution is like basically multiplying all those together. And then for the denoising process, we essentially reverse the Markov chain. So reverse the forward process. And this is not something we can just mathematically derive. There's a whole math proof for it. We actually need to estimate it using numerical techniques and like inference. And here is the Markov chain adding noise. So essentially, the first term in the normal distribution brings the mean closer to 0, and the second term basically increases the standard deviation. And the B is basically how much noise we add at each time step. And we increase the amount of noise we add as we go forward because we want the final steps to essentially be adding a lot of noise so that when the model denoises, it learns the general features first and then it learns the more niche features to add. And yes, so go ahead. Oh, forward. Forward, please. Now, our approach, we're going to combine quantum RBMs and diffusion models. So one application of RBMs is denoising images. We can train RBMs to remove noise from images, essentially. So we had the idea, why not replace every step that removes noise from the noisy image in our model with a RBM that removes the noise? So we would have an RBM there, removing noise, RBM there, and they all just remove noise in a chain. So this is our model. So we take an image, we pass it through a convolutional neural network autoencoder, not UNet, and we get a binary vector representing our image. Then we add noise to that binary vector using a Markov chain type process, and we get a noisy binary vector. Then we remove noise from the binary vector using a chain of RBMs. And each RBM removes noise, removes noise, removes noise, and reverses this process until we get a binary vector that represents an actual image in our data set. And then we use our decoder to go from the binary vector to an actual image. And the reason we have to make it binary is because, well, an RBM uses binary nodes. And this is how we add noise to the RBMs. You guys can check this out later. For the sake of time, we will not go forward, but essentially it converges to a Gaussian distribution, and it is a Markov chain. So, and why do this? Well, as Jeffrey mentioned, quantum RBMs are a lot faster than classical RBMs. In fact, they take microseconds, which is like a millionth of a second. So it's essentially negligible. So, and in fact, okay, and yes. And with that, so to generate one image, our model takes around 0.4 to 4 seconds. This is based on hardware estimates regarding a quantum annealer. So this is comparable to classical models. However, where our model shines is when we try to generate more images from the same noisy distribution. Say we try to generate 10,000 images from the same noisy vector. The constraint with quantum annealers is not the quantum part, but the classical part, essentially setting the values of the nodes, setting the values of the weights and the biases. If we essentially generate from the same noisy distribution, we have to modify the quantum annealer a lot less. And this removes a lot of the classical overhead. And in fact, we did our calculations here. And for the sake of time, we're not going to go into them, but essentially it will take 1.13 hours to generate 10,000 images of any size, as long as that size can fit onto a quantum annealer, of course. And compare this to a classical model, a classical vanilla DDPM. Here we describe the model, just your classic DDPM, no enhancements, no acceleration with the Markov process. We assume 2 to 6 seconds per image generation, and a classical model would take 6 to 18 hours. So compare that, 1 hour to 18 hours, 1 hour to 6 hours. Our model offers a substantial speed up. And now I know what you're all waiting for, the tests. Well, here are the tests. We ran it on UTMIST. For the sake of time, we'll just skip over this, but one important thing to clarify is that we used a lot of Gibbs sampling steps per RBM, and we used a lot of contrastive divergence steps because the whole idea is that with a quantum RBM, we can run more of these steps in the same amount of time, leading to a better estimate. The results, well, this was 10 minutes of training on the train this morning, but it's promising, shows that our model works. Now let's see more complicated images. We used it on airplane data. Next up. And here are airplanes. So once again, this was around 20 minutes of training, but it shows a proof of concept. Our model works, and some images are pretty bad, some are all right, and yeah. So, and here's the autoencoder training.
Actually, that concludes our presentation today, and hope you guys enjoy. And we're open to questions, and if you guys have any questions.
So did you learn a different model or a different set of parameters for each step of the denoising process?
That, guess that's for you to answer.
Yes. Apologies, we kind of skipped over this, but we mentioned like we denoise the image using RBMs. Yeah, we have a separate RBM for every time step. So say we add noise 50 times, we would have an RBM that reverses the noise at each of those noise additions, and it would train it separately.
So the noise distribution at each time step, is the noise distribution the same for each time step?
Could you clarify that?
My impression was that you run it through, like, you're adding noise multiple times over multiple steps, right? And you'll reverse that noise over multiple steps. Is that correct?
So you're asking if we add the same amount of noise at every step, or? Uh, you actually increase the amount of noise you add as you go up in the steps. And the reason why we do this is we want the last few set of steps we want to add a lot of noise in those steps so that when our model reverses those steps, it's kind of forced to learn the general features because needs to remove a ton of noise. And to do that, you need to know the general features rather than the niche features, which you want to learn later. Does that address it or? Okay. Thanks for the question.
We'll take like one more question due to time constraints here. So,
Hey, nice update. Michael told me about this. I guess in the fall as well. Could you walk me through kind of the design space there? So, it seems that you're saying that you sped up sped up specifically optimizing the RBM. So I guess my question is how much? And then the other question is, how does generating using the RBM compare to the alternatives?
so maybe I can answer that in two separate answers over there. So for the first one, how fast it gets. So regarding that, so there are literature saying for quantum annealer using on VAE, that thing got accelerated by 100 times comparing to classical models, benchmarking models. And second, regarding is the second question regarding the quality of the image? Okay, so actually for our project, because it's still ongoing, so there's a lot more to improve, a lot more to verify. We don't have like a numerical value so far. All I can pull out is art from literatures that we have done, and you can see that the qualities of the quantum annealer comparing to other Markov chain Monte Carlo sampling methods.
Yeah, so I guess like the 100 times, that depends on the size of that's got to depend on the size of the image, right? So
Right.
Do you know what it is in terms of the complexity?
It was really complex. So the thing I was referring to is referring to a like a project my friend did. They published the paper on that already. So they have they were working on high energy particles, and they have a shower of high energy particle, and that's very very tiny and highly accurate. So I would say the complexity is huge, and they still have 100 times accuracy and improvement. Thank you. So yeah, if there's no other questions, I think that concludes our presentation today. And thanks you guys for being with us here.
So next on the podium is going to be the Deep Emotion team, which is our second last team of the night.
All right, hello everyone. Okay, so we're the Deep Emotion team. We've spent the last bit of time training convolutional neural networks to classify naturalistic emotion from 7 Tesla fMRI data. I'm Josh.
I'm Samuel.
I'm Toya. Go ahead. So our main motivation of our project is to confirm our functional understanding of brain's emotional responses, and more importantly, to teach our models to learn these emotional representations. Ultimately, we hope that our findings can be translated into clinical practice in mental health care. Next slide. So we are using Forrest Gump dataset. For those who may not know, this is a public fMRI dataset that captures brain images of 20 different subjects as they watch the movie Forrest Gump. The dynamic and continuous narrative of Forrest Gump elicits spontaneous emotional reactions from subjects, which are crucial for the model to learn how emotions are processed, how we process emotions naturally.
I want to add quickly here that this data set is ubiquitous in the neuro community for being one of the largest naturalistic data sets for fMRI data. So a lot of fMRI tasks are on like tasks that try and distill the input to the atomic cognitive function. And what's special about this data set is it's lots of subjects and they're watching a movie, so it's more like how their brain would act in real life.
So here's our high-level overview of the model pipeline. We begin by processing each 3D slice of a brain image using 3D convolutional and max pooling layers to extract low-level embeddings. Then these low-level embeddings are fed into a classification head to produce one encoded emotional label, such as sadness.
Yeah, so this is how our annotations look like. So if you look, each row corresponds to a set of fMRI images. And so listed is the start and end time of when these fMRI images were taken relative to the movie that they were watching. So the start and end times in the movie. And then our main column that we were focusing on was that emotion column over there. And as you can see, that each scene is labeled with an emotion such as love, pride, compassion, etc. So in order to consolidate the amount of emotions, because there were around 20, we identified 5 principal emotions that occurred most frequently, and then we used a co-occurrence matrix because there were eight judges that at the same time had annotated the movie, and so we used a co-occurrence matrix to identify which emotions could be grouped together based on the amount of judges that frequently chose that emotion for a given scene. So over here is just an example. So let's say for a given scene, there are 8 judges. They identified the emotion listed over there. We would take the emotion that was most agreed upon, and then we would put that as our label for the aggregated annotations, and then we would also have another criterion. We would need that at least 4 judges mentioned this emotion in order for it to be used. And if we didn't have agreement with at least 4 judges for that particular emotion, then we would just put a none label.
So at low level, our model consists of 3 convolutional layers to extract 3 convolutional layers and 3 max pooling layers to extract pixel level information from a brain image at a given time step. The classification head consists of 2 convolutional layers. We configured our data loaders to provide small stochastic mini batches on each subject and removed non-labels to prevent model from cheating by producing a meaningless output. We trained our model for 50 epochs using Atom Optimizer with a learning rate of around 1e-4 to ensure steady loss convergence. So here are the training results. The left graph shows the average accuracy of 20 different CNN models, each trained on each individual subject. And the right graph shows the accuracy of one model trained on the full data set. As you can see, the both performances are remarkably similar. However, next slide, the left messy visualization shows that cross-subject model does not always outperform some single subject models, meaning that there is a variability in models in emotional classification between subjects.
Okay, so what you're looking at here is our inference results on all of our different models to held out data. So to read this graph, The row is what emotion label is the held out data, and the column is which model. The color coding is the model accuracy on that held out data. So just to pick an arbitrary square here, this is the model trained on only subject 14. This is its performance to held out data on with the label happiness, and we can see that it gets about 0.8% accuracy on held out data with the label happiness. So I'm going to give you some time to look at this graph because there's a lot going on here. But actually, in this one graph, there's a lot of neuroliterature results that have been accumulated over the last couple of decades that just can immediately be pulled out of our graph, despite the fact that this model is completely brain agnostic. So the first thing I want to point out is that there's a lot of variation between individuals here. So, you know, this individual, the model struggles with love and anger. Similarly, for this individual, different individuals, the model was able to completely classify which emotions they were experiencing for held out data. This is pretty well established in the neural field that human fMRI data has different signatures for different emotions. Emotion is highly individual. It's this, like, the theory behind this is that emotion is learned. So it's believed that your understanding of emotion comes largely from your parents and different partners that teach you emotion. And this immediately is something that we can pull out from this chart. Okay, another thing I'd like to point out, the top row is completely green, and that corresponds to fear. Well, similarly in the neuroliterature, we know that fear has the strongest and most consistent signal of these emotions. And likewise, this is something that we can immediately pull out from this graph, despite the fact that these models are brain agnostic. And also, I have citations that will that point to these results in the literature. Okay, the last thing I want to point out with recreating neuroliterature is that this cross-subject model really struggles on love. So if you look at the different emotions here, it does well on fear, sadness, happiness, and anger, but it really struggles to generalize love across different subjects. Well, it's pretty well established that we shouldn't consider love as an emotion because love in particular is highly variable and is shown to be something that's very learned, something that is taught to you by your parents, and is not so hard-coded in the brain as other natural responses. And it's really exciting that this result just is immediately pulled out by our model despite it not knowing what a brain is or what the data is that's looking at. Okay, so moving on, just some interesting caveats with this graph. The subject 19 model, like you might notice, had the worst performance of any grid space here. And so in particular, the model that was trained on only subject 19 identified the scenes in which this person was viewing a love scene with below 0.2% accuracy. So first of all, we're giving some basic demographics about this individual. All we are told is the age and sex of this person. So we were informed that this person is 22 and identifies as a woman, which stay safe out there, fellas. And if we look closer at what our model told us that this person was experiencing during these love scenes, we can identify that they were mostly experiencing sadness and also some happiness. So I don't want to extrapolate to like, you know, I'm not gonna draw any conclusions about this person. We perhaps that they had a breakup earlier that day. Perhaps this is indicative of something else. But really, the key takeaway here is that this model, like the inference, is very powerful, and it like, you know, motivates further clinical applications possibly without drawing any generalizations about this particular person. Okay, moreover, we wanted to test if our model can generalize to unseen subjects. So these are 4 different models trained. This one's trained on only subjects 5 through 20. This one's 1 through 4 and 11 through 20 and so on. And you can see that they just completely collapse on held out subjects. So this is a disappointing result in some ways, but it's good to know. For me, the impact here is the consumer application, because if we have consumer products that try to classify your emotion without ever having trained on this consumer, this person, then you can see that a lot more work will be needed in order to perform inference on someone without training on their particular fMRI signature.
Here is a slightly more interpretable result. So we used MedCam, it's a GradCam for medical images, to create heat maps to show where the model is attending. So the heat map is based on the magnitude of the gradients of the input classification tensor. The heat maps contain some artifacts, as you can see, like the lines extending beyond brain boundaries, which shouldn't happen. So our next step is to refine our CNN architectures to yield more interpretable results.
All right, thank you. And I think we might have some time left for questions. Awesome. Yeah.
I'm sorry if I missed this earlier, but what is your main goal out of this solution? Like, what are you looking for and achieving?
Yeah, so our original goal was just to do a big machine learning project on lots of fMRI data. And the reason that that's worthwhile is because in the neural community, like the neural community is a little late to adapt to these big data approaches. And like the reason this study forest data set is even valuable in the neural community is most neural data sets are from like maybe a couple of subjects and they're training on like really like they're like for example vision is very high studied in the neuro community, and so they're looking at lines and they're trying to distill like what is the brain doing for this like really small thing. So the novelty here is that this is a huge data set and it's naturalistic data and it's totally generalized across tons of subjects, and like our motivation was really just to bring big data and machine learning to an area that's a little behind with that and see what we could do. And I hope I've shown you that that approach is valuable and that using inference, maybe there are some clinical applications here. Maybe we can learn more about how brains like represent emotion using interpretability mechanisms. But the real motivation was simply to bring ML infrastructure to the neural community.
Great question. Thank you.
I'm actually just a comment. I'm quite surprised that when you train the cross subject models, that fear wasn't learned through like across the participants. I'm wondering if you could think about ways to, or not this one, the one after one. Next, yeah, this, yeah, that's.
Oh, this one?
Yeah, yeah. Do you have any comments on why you think this would be? Because I would assume that fear would be a pretty noticeable trait in fMRI data.
Yeah, I totally agree with you. And I was surprised by this result too. And this was results that we gathered somewhat recently. So we have a supervisor who's a neuroscientist who's helping with this project. And he helped us explain some of the early results, but he hasn't seen this yet. And this is like a really good question. And the short answer is I don't know. And this is something we need to look into. Yeah.
Maybe you could try training on 19, testing on 1. So just like leave one out.
Yeah.
Validation, see that.
I think that would be a really good thing to try. Yeah.
We have time. Yeah. Sorry, another question. If you had to collect more data, because you're saying so basically, I mean, it's 20 subjects, which in the context of neuro seems like a lot, but in global context, not that many. And I'm guessing, like to some degree, they probably try to diversify the subjects as well. But if you were to collect more data, what would your approach be to actually see if there is like broad kind of spectrums that you can pull out, or things you can pull out of like fMRI data on emotion?
So you mean specifically fMRI data?
Yeah, like specifically, would you just is the solution just to collect massive amounts of naturalistic fMRI data? Is there a more niche experiment so you can like try to actually like tease out something? Do you have any ideas on approach to that?
Yeah, so I think like part of what I've demonstrated here is that there's lots of different approaches we can take. And so if you're particularly interested in understanding more about emotion, I actually think that there might be some limitations with the naturalistic approach. So I think that if you were really trying to understand the neurotheory of emotion, it might be better to move to a less naturalistic space. But personally, if you're interested in big data, I actually think that a less invasive
Yeah.
data set and like there's non-invasive, more commercial brain imaging stuff like ECG and wearable ECG neurable headsets and stuff like that. So that I would be really excited about that. In fact, there's a company called Neurable in Boston, and they have a headset which is trying to get your emotion and like recommend you music based on how you're feeling. So it's like not, totally non-invasive, but like you could have tons of users, so that'd be really exciting. And they want me to wrap up, but thank you. Thank you all for the questions.
Thank you.
So now we're going to welcome to the podium our last presentation of the 2025 showcase, Flow to Learn.
Okay, so hi everyone, I'm Daniel. I'll be sharing our project, which is Flow to Learn on using flow models for weight generation. It's just me, so I guess we'll get started. So I guess beyond the interesting idea of just using neural networks to learn about neural networks, so you have, I guess, more conventional use cases, such as for instance, in like large language models, you would like use examples to improve on later prompts, or I guess to give examples for how to complete your prompts. And essentially, we can use this method to extend this, say, to the image domain. So I guess that's one conventional application, but more generally, this can be situated in, I guess, the meta-learning literature. So, which is basically using the same training model to train on different tasks. And as a research question, we can ask like, does our method sort of perform well in these like typical weight generation experiments, and does it enable typical applications like few-shot learning? So I guess one other thing to note is that we flow on latent space, which means we have like an encoder decoder architecture somewhere in there, and we'll later show that performs well on like weight generation and some few-shot learning tasks. I guess to provide like a brief outline of what flow matching is that it's like a generative method that learns a vector field between distributions P0 and P1. So the blue here is P0 and the red here is P1. Unlike diffusion, which is what we're comparing against, is that we're not restricted to, let's say, Gaussian noise as a source distribution, which is P naught. And we can make use of that pretty much immediately by basically using weight initialization, such as chiming normal as a source distribution. And that, in a sense, provides another degree of freedom in the flexibility of modeling a weight evolution. And I guess one other thing is that it's a bit more efficient and more direct as to how you optimize things. So an outline of like how the training would go is that you would sample x0 and x1 from P0 and P1, then you draw a straight line and you match the velocity to that straight line. And so in an ideal world, you would imagine samples from P0 will just move in a straight line to P1. That's basically how inference goes. The general workflow is something like this, where you have an encoder and decoder setup, and you have the flow meta model in the middle, which is the main generation model. We can do different inputs as to how we pass into the encoder. For example, if we use like a VAE, we can vectorize weights and then pass it in to the encoder. But we also have something like a graph encoder, which takes into account like permutation symmetries of the neural network, in which case we would have a graph as input. And okay, this first experiment is, I guess, the most basic thing that one can do with weight generation, which is that you train like a variety of like base models on known data sets. In this case, we have these four. You can save a bunch of weight checkpoints, and then you train a flow model to generate these weights. So in total, you would have 4 flow models at the end of it, and then you just validate these generated weights on the test set. The numbers themselves here are not too important, just that you can see that our method, which is in the middle column, matches original training and a diffusion baseline that we found. And so we can sort of see that it has the capacity to learn how to generate weights. And this next experiment sort of expands on that, because the previous setting was quite restrictive. You need to fix an architecture and you need to fix a data set. In this case, we provide a degree of freedom in the data set dimension. So, so essentially what we're doing here is we're fine tuning the meta model, is the model that generates the weights. And how we do it is basically how you would do normal fine tuning, which is you take a pre-trained model, you take loss and back propagate, and then you see what happens. And this last point is about how we do inference. So as you recall, how what we're training essentially is a velocity field, and so we do inference by solving an ODE. But typically in practice, this will take a lot of function evaluations. And so one way to expedite fine tuning is you would stop gradient flow at some point during the ODE solver. And so that's the last point here. And you can see that, okay, the S suffix is like a static model and the F is a fine tune model, especially for the CNN. You can see like a big improvement when we do the fine tuning. And another thing that we can append to our model is a dataset embedding module. So in this case, well, previously our meta model has no sort of idea of like what we're classifying with the weights that it will generate, but here we provide this conditioning information through a context image embedding. And this next experiment makes use of that. So in this case, we have 100 weight checkpoints from a model zoo for each of the 4 data sets here. And we train the flow model on the 400 total base models, conditioned on samples from each of the data sets. And so we just generate the weights as normal and then do validation and so on. And we see that when we test with like a random sample from one of the 4 data sets to condition the model, we can see that it actually generates weights that provide slightly better accuracy than the original. Original just means like conventional training. You can ask me about the prior afterwards, but yeah, that's just a slight deviation from what we're doing. And then another sort of extension of the previous experiment is just that in this case, we're taking weights instead of from epochs 46 to 50, we're doing epochs 21 to 25 to have like some room for improvement. And then we generate the weights using our method, conditioned on support samples, like in the previous experiment. And we use that as like a sort of initialization for fine tuning with the same data set. So you can, and we're comparing with like a random initialization. So you can, like as expected, at epoch 0, we have like random chance for random init, but we sort of start quite high for our method. And you can see it sort of converges a lot more quickly as we go through the epochs. And the data sets with an asterisk, those are out of distribution data sets. So in the previous slide, these are the only 4 that was trained on. But the 3 at the end are out of distribution sets. But even with those, you can see that convergence still happens faster. And so that's one, I guess, interesting application of this method, that it can be used as a sort of weight initialization during fine tuning. Okay. And this is our last experiment. It's the most preliminary one, but I think it's, I guess, the most applicable thing that we can do, which is feature learning. To give like a brief outline of what the setup is that we typically have a bunch of episodes, which are composed of support images and query images. And the meta model, which is our flow model, is conditioned on the support set images and generates weights for the query images. The analogy to like large language models would be that the support set is like examples that we provide, and the query image is like the prompt that we're asking it to do. And here are the episodes, well, not in this figure, but what we're doing in training is that they're composed from many ImageNet data. But we're ultimately interested in training a model on a large enough data set that we can do feature learning on episodes from out distribution data sets. So this is like a very preliminary test on CIFAR 10 and STL10, which is not what it was trained on. It was trained on mini ImageNet. And you can see that it performs a bit better than the CIFAR 10 dataset, and a bit worse than the fusion model baseline that we tested against. But I guess this is quite promising, as our VAE reconstruction has quite a high base accuracy, which means that I guess with a bit more tuning of the training procedure, we can hopefully get up to what we have in our VAE. And I guess that's a segue to what we're doing for future work. So as I said, we're probably going to train our method on more larger and more diverse data sets, especially for few shot learning. And as for our fine-tuning procedure, what we did was we just did like backpropagation, but we can make use of, let's say, more recent methods on reward fine-tuning for especially challenging data sets like medical imaging data sets. And this last point, I think, is interesting as it's also something that before we started working on, which is sort of controlling the inference trajectory. So I'll just say a bit more on that last point. So from the usual flow matching procedure, we sort of match these straight lines between the red dots and the blue dots. But you can see from the plot here that the blue regions are regions of high loss. And so if we actually go through the straight lines here, we will sort of enter these regions of high loss. And if our training is imperfect, we may sort of like stay in that sort of well. And so what we actually want to do, and what we're doing instead, is that we save weight checkpoints, which are these like green dots during training, and optimize the best fit curve connecting P0 and P1, the source and target distributions. And instead, we match our velocities onto the curve gamma, which in that sense, it goes through the purple contours, which are regions of lower loss. And if you know a bit more math, this is like constructing a Riemannian manifold with the metric being like the norm is low when it's close to the green points and large ones further away from the green points. And then the curve gamma is the geodesic between sample points P0 and P1. And yeah, that's about it. I guess we can take questions.
Give a bit more context on the kind of current state of the field on the sort of meta model training right now. Like how large can meta models get, and what type of models are they currently basically generating weights for? And how big was your model as well? I don't think you exactly specified, like, for example, number of weights that's actually generating.
Yeah, so I guess we can have, I guess, two measures of size here. You can either measure it from the number of data sets that you're able to generate weights for, or just the size of the architecture that you're generating. In that sense, we can actually go, in the sense of the architecture size, we can go quite high, but the limit there is computation. So for example, you can actually generate like transformers, but those take a lot of time. I think the more interesting question is like whether how many data sets you can generalize to, and in that case, there are, as I said, there was a diffusion model baseline that could, in a sense, generalize to like I think they did like 3 different data sets. They tested on 3 different data sets at least. And as for our model size, we just use like a UNet. It's like basically what you would do in diffusion, but we just applied here.
Okay. So I guess just to specify again one question. Do you know in the field how big of a model, like how many parameters have they generated?
How many models, how many parameters have we generated?
No, like in the field, in the state of the art of the field, for example, how large of a model have they generated? Because like you said, you can generate anything, but it's like a computational issue.
Yeah. So I believe we can generate like small transformers, which are in the regime of like 80 million parameters.
Cool.
I think that's what I've seen at least.
Cool. Thank you so much for the presentation.
There's nothing.
All right, is everyone ready to find out the winners of the 2025 Winter Showcase? There we go. All right, so now I'm going to pass it off to our judges so they can announce the winners.
Okay, so first up is most innovative, and this is kind of the criteria we're going by. So we want something that's unique, novel, is trying to do something cutting edge, pushing the state of the art right now, or what already exists. We want you to approach it in a creative problem-solving manner, and try to make something new and not just do something off the shelf or copy a different product. And then in terms of advanced techniques or technologies, how complex is your solution? How much advanced methodology or tech did you have to go learn and implement and actually try out to make this? So the team that did this, in terms of unique concept and approach, like they melded together 2 kind of cutting edge things of generative models and diffusion models along with quantum computing. The approach to actually formulating the problem and actually setting up the theory and the entire pipeline was very interesting and good. And then in terms of advanced techniques and technologies, I think both the understanding of the mathematics behind how diffusion models work, but also how the Boltzmann machines work was very well done. And then clearly the implementation does fairly well as well. So I think you can guess that the most innovative is QDiffuse. Oh. Congrats. Thank you. It says the pink guy. Oh. All right. Yeah. Yeah. Oh.
Awesome. Congratulations.
Okay, so up next, we have the award for most impactful. So our criteria here was one, potential for real world application. Did you make a connection to how your proposal would be used in the real world? Societal or environmental benefit? Did you make a strong case for how meaningful and your application is? And then quality of implementation. So could we see that you took into consideration how your product would be used in the real world? Did you discuss some of the pros and cons in there as well? So the team that won for this one had a very compelling value proposition. They did a very good job of articulating how their idea connects to a real world application, a meaningful application, that being healthcare. And they were also very open and honest about their progress, but still maintained high hopes and articulated their ambitions for the future as well. And this team was not Deep Emotion. This team was RNA Folding. Sorry for the slip up.
Okay, and for the last category, we have the best presentation. Although we got lots of great presentations today, great job, everyone. The team that we selected is the team who delivered the most concise presentation, and they were very engaging. They asked the Q&A, like the Q&A questions in a very clear way. And that team is Deep Emotion.
No problem. Thank you. Thank you so much.
Do you guys mind scooting in just a little bit and coming back from up behind the podium? Thank you. So that concludes our 2025 Winter Showcase. And first of all, I want to give a warm round of applause and thank you to our judges for their generosity and insight and time to the presenters today. So if you all could give them a round of applause. And to all the judges, we actually have prepared some gift baskets for you, which Sneha is going to hand out. So we hope you enjoy these along with your UTMIST hoodies. Come again next year. And so next, I would like to thank all of our UTMIST project teams that represented their work up here today. For the past 6 months, they've been working diligently to make their projects a reality, so please give them a round of applause. And now finally, I just want to thank all of you for coming for this event today and supporting the work that we do here at UTMIST. We know that for many of you, it's the midst of exam season and the last day of reading week, so we truly appreciate the time that you spend here with us today. And so now I'll just be passing it off to our co-president Matthew to talk about some of our upcoming events.
Also, could you give a big round of applause to Rachel and the different directors of the engineering team for doing such a great job organizing this event? Yeah. Okay, cool. Yeah, while I have the stage, I just wanted to briefly share some of the other things happening within UTMIST. While the semester is halfway through, there's still a number of events, some of the UTMIST even largest events, that are still kind of down the line. So one of them is QCI, that stands for the Canadian Undergraduate Conference on AI. So this year, it's happening in Toronto in the Mars Building just a couple weeks from now. So if any of you are kind of interested in presenting some of your work here today, or different ML projects that you've developed at this conference, as well as networking with a bunch of different people. I know they have people from Vector, Anthropic, Meta, Cohere, a bunch of different representatives, so if that sounds like something interested to you, highly recommend checking it out. And for all the different UTMIST internal teams, we'll also be trying to connect you with forms of reimbursement through NSOC and Department of Computer Science, so to help you kind of, navigate through those kind of financial roadblocks that might be there. So that's QCI for you. The other one is the SciML workshop. So if any of you are interested in ML applications within science or research in physics, highly recommend checking out the SciML workshop. This will be happening from March 7th to 28th every Wednesday. We're also, for our last session, going to have a special guest speaker, Ben Mosley, who is ex-head of machine learning at NASA. The other thing is AI Squared Tournament. I know some of you were involved with it this past 2 weeks, but the tournament is still ongoing for those of you who are not familiar with the tournament. Essentially, everyone has an opportunity to build an AI agent to kind of participate and play in this AI kind of like platformer-based game, similar to Super Smash Bros. Or Brawlhalla, if any of you are familiar with those games. So the final tournament is occurring on this Friday. So if any of you want to check it out, there'll be a link in our link tree to join the Discord. And then once you're there, you can all the instructions are there. You can create a submission and see how the finals go. And finally, our last major event is Gen AI Genesis Hackathon. So this is Canada's largest AI hackathon. We're partnering with Google Developer Student Group, CSSU, and U of T AI to make this happen. At this event, we'll have partners and representatives from Google, the United Nations, AMD, Cohere, and many more large tech organizations. I highly recommend you check it out, especially if any of you are interested in generative AI, as we'll have special guest speakers from Google talking about how to use all their different APIs, as well as key mentors and people from industry helping you out. So yeah. Also, last thing, for those of you who haven't seen it, we have UTMIST merch. Hoodies are all like 10% off today, so normally they're 50. Today they're going to be 45. If you want to try to negotiate a deal with me, that is also possible. We'll see. We'll see. But yeah, if any of you are interested, hoodies are just up front. I'll be there after this during networking. Yeah, I think that's it from me. Passing it back to Rachel.
Thank you, Matthew. And so, yes, if you'd like to stay connected with UTMIST, this is a QR code that has a link tree with some of the events that Matthew just spoke about. And now we're going to go into a bit of like a networking session so you guys can like chat with each other. Feel free to head out though if you have somewhere else to be. But I would like to ask some of the winning teams to come to the front so we can just take some photos of them and have some memories. But thank you all so much for coming today, and we hope you get home safe with the weather.